Welcome to your Chapter 15 video for Gen Chem 2. This one's all about equilibrium, is what Chapter 15 is for. And equilibrium is a very interesting process, happens all through nature and all throughout the universe, as a matter of fact. And what it is essentially is two opposing processes that take place at the same time at equal rates. Right, so in Chapter 14, we learned all about rate laws and determining rates and all of this sort of thing. Well, when we reach an equilibrium, two opposing processes, the forward and back reactions, are happening at the same time at the same rate. So forward and backward reactions are equal in their rates. And we dealt with that a little bit when we were looking at reaction mechanisms, where we had the example of having a first reaction that had an equilibrium and a second reaction that had a fast step, and you had to account for both the forward and back reactions in order to substitute in for the intermediate, right? So in Chapter 15, we're going to dive real deep into aspects of equilibrium. And a really common and simple example of equilibrium is boiling water with the lid on the pot. Okay, so at the bottom of the pot, you have your liquid water. At the top of the pot, you have your gaseous water, okay, water that has been boiled away and is now in the gaseous state. And so what's happening all the time when you're boiling this water with the lid on is some of the water molecules at the surface are becoming gas. And at the same time, those gas molecules are condensing back to liquid. Okay, because down at the bottom of the pot, things are hotter, closer to the burner. That should be an E. And up at the top of the pot, things are a little bit cooler. All right, so cool gaseous water at the top will lose some energy and condense back to liquid, and then it gets into the liquid, drops down close to the hotter portion of the pot, gains some energy, comes back up, and becomes gas again. And so all of this is happening at the same time at the same rate, because if we have the lid on the pot, then none of that gas can escape. If we left the lid off, then eventually we would boil all the water away and it would all be in the gaseous state. And then right at the surface of the water, just above it, we have the vapor. This is our vapor pressure. We talked about that in Chapter 14 as well. Okay, so liquid becomes vapor at the same rate, that's important, that the vapor condenses back into the liquid. Okay, so thinking about how this applies to our chemical equations, what we're going to need is, as a very basic skill, is writing an equilibrium constant expression. Okay, so this term equilibrium constant. So every equilibrium has a constant that goes along with it, and it's related to the equilibrium concentrations of the reactants and the products. And as you might guess, the symbol for the equilibrium constant is K. Big surprise there. Okay, so K equals the products raised to their stoichiometric coefficient. And we're just going to say stoich for short, divided by the reactants raised to their stoichiometric coefficients. Okay, so if I do write a sort of generic reaction, let's see what an equilibrium expression would look like. So if I said, and we saw this before, A of A plus B in equilibrium. Okay, that's what the double arrow is talking about, with C for C plus D for D. Right, if I write an equilibrium expression for this reaction, products over reactants raised to their stoichiometric coefficients. So I'll say K equals concentration of C raised to the C power, concentration of D raised to the D power, over A to the A power, B to the B power. Okay? These are my products. These are my reactants. Now, when we were writing rate laws in chapter 14, we were really only concerned with the reactants. When we deal with equilibrium, because we're dealing with forward and back reaction, we have to consider both the products and the reactants. Okay, so this was a generic example. Let's write one that's for a specific equation. Take a look at how that looks in sort of, for lack of a better term, real life. Okay, so if I have a redox reaction, copper 2 plus aqueous plus some tin ion aqueous in equilibrium with some copper plus aqueous plus some tin 4 plus. Okay, so if I wanted to write an equilibrium constant expression, first I need to notice that I have this double arrow. Okay, I can't write an equilibrium expression if I don't have that double arrow. Okay, if I only have a single arrow, it's not an equilibrium. Okay, so the equilibrium expression for this particular reaction, products over reactants raised to their stoichiometric coefficients. Now I wrote this particular reaction because it has ions, and I want you to focus on the stoichiometric coefficients. Okay, we don't care about ion charges, right? That's just a description of a chemical species. All right, so if I write the equilibrium constant expression for this reaction, equilibrium constant expression, right, I'm going to say K equals products over reactants. So I'll have my copper plus squared, because it's has a stoichiometric coefficient of 2, times my tin 4 plus, and it has a stoichiometric coefficient of 1, right? So it goes to the first power. I don't have to write that power, okay? Over my reactants, and I have a copper 2 plus to the second power, because its stoichiometric coefficient is 2, times my tin 2 plus, which has a stoichiometric coefficient of 1. Okay? Products over reactants raised to their stoichiometric coefficients. Right? Now, writing the equilibrium constant expression is going to be super, super important. Okay? You need to be very skilled at this, very confident in your equilibrium constant expression, because as we move through the chapter, that's going to become a very, very essential tool. Okay? Now, another interesting thing, and kind of important, is that this actually comes from activities. Okay, and activities are useful for when we're dealing with non-ideal behavior. All right, so in the example above, the equilibrium expression is in terms of concentrations. But really, if I wanted to be very, very careful about how I write this, I can write it in terms of activities, and the symbol for activity is just lowercase a. So I'd write this as activity squared for copper 2 plus, or excuse me, copper plus the activity of tin 4 plus divided by the activity squared for copper 2 plus the activity for tin 2 plus. Okay. Now, I want to make it clear that you do not need to know how to write the expressions in terms of activities. The reason that I show this is for this reason, is that solids and pure liquids have activities of 1. Okay, so if their activity is equal to 1, then they don't have any bearing on the equilibrium constant expression. So very, very important. Solids and pure liquids don't appear in the equilibrium constant expression. Okay, so phases of matter in your chemical equation are important in this chapter. Right? It's really common for us to, sort of, okay, there's phases there. It says aqueous, solid, liquid, gas, whatever. Solids and liquids do not go in the equilibrium constant expression. Okay? So how do we use this? We're going to use this form of the equilibrium constant expression for this entire chapter. Okay? So we don't have to worry about this activity thing except in the knowledge that the activities have to do with solids and pure liquids. Okay? So let's see how we can use this. So let's say we've got our equilibrium expression for the reaction we've been looking at. All right? So we have K equals the copper plus squared times the tin 4 plus to the first power over the copper 2 plus squared times tin 2 plus to the first power. Okay, so let's say we know K and some of the equilibrium constant expressions. Okay, before I go any further, I need to be clear that these concentrations are concentration at equilibrium. Okay, so if we are talking about K, everything in the K expression is at equilibrium. So if I wanted to, I could say K squared EQ, tin 4 plus EQ, talking about equilibrium constant expressions, equilibrium constant concentrations. Okay. So to continue on, sorry for the pause there. This happens to me in the classroom all the time. So let's say that I know K and some of the equilibrium constant expressions. Right? So we have this equilibrium, concentrations. Okay. Let me just continue on. So let's say we have the value for K. K equals 1.48, for example. And copper plus at equilibrium is 0.148 molar. The tin 2 plus at equilibrium is 0.124. And we know that tin 4 plus at equilibrium is 0.176 molar. Okay, so the question is, what is the equilibrium concentration of the copper 2 plus? Okay, so we have everything from our equilibrium constant expression except for the concentration of copper 2 plus. So all I need to do is plug these values directly into my expression and we can solve. So I have my expression EQ, tin 4 plus, EQ divided by the copper 2 plus squared okay, and we're given the values for most of these things. So the value of K was 1.48. We have 0.148 for this one, 0.176 here. We don't know this one, and we have the 0.124 for that one. .48 equals 0.148 squared times 0.176 over the copper 2 plus squared and 0.124. All right, so we rearrange and solve, and we get to a point where we'll see the copper 2 plus at equilibrium equals the square root of 0.0210, 0.145 molar. Okay, so hopefully that arithmetic is not confusing to you. It's worked out in a little bit more detail in the handwritten notes in modules, so if you wanted to see that math, you can certainly take a look at that. I know a lot of you are looking at the handwritten notes, so that's a good thing. So let's take a look at the relationship between the equilibrium constant and rate constant. So I mentioned earlier how things, we're talking about rates of forward and back reactions. All right, so let's see how our equilibrium constant relates to the things that we already know. Okay. And so this equilibrium expression doesn't just conjure out of thin air. It actually comes from what we know about how to deal with rates. So if I've got my lovely generic reaction again, in equilibrium, and we have a K1 and a K2, K forward and K back. It's related to G plus H for H. Okay, and let's assume this is an elementary reaction. Okay, so my orders of each component are directly related to their stoichiometric coefficients, right? So if I write the expression for the rate forward, will take the form of rate equals K1 A to the A power times B to the B power, right? Because they're elementary reactions. Remember that's why we're saying A to the A, B to the B, right? So our rate back will be rate equals K2 G to the G power H to the H power, right? So we're talking about equilibrium. So our rate forward equals the rate back, right? So I can write this as an expression where I put these two rates equal to each other. So I can say K1 A to the A power, B to the B power equals K2 G to the G power H to the H power. Okay? So now let's take and solve for the rate constants, right? Oh, stop. Sometimes this program solve for the rate constants. All right, so I'm going to rearrange to get all the k's on one side and take a look at what we get. K1 over K2 Doesn't this look interesting? Products raised to their stoichiometric coefficient over the reactants raised to their stoichiometric coefficients. Right? And so we can just say, like we did in chapter 14 when we were rearranging and solving for intermediates, we can say K1 over K2 just equals big K. Right? So this knowledge of the equilibrium constant comes from our knowledge of rates. Okay? So, like I said, it's not conjured out of thin air just to be arbitrarily mean to students to try to make you work it out. So let's take a look at, let's do some practice with equilibrium constant expressions. Okay, so let's say we have a reaction that looks like this one. Two NO2. Right, notice we have all gases, right? Gases are fine to go in the equilibrium constant expression. So my equilibrium constant expression for this reaction will look like this. K equals NO2 squared over NO squared times O2 to the first power. Okay, because we have our stoichiometric coefficients of 2, 1, and 2. Right? That's how we get the powers in our expression. Right? That was an easy one. Let's take a look at another one. Let's say I have some zinc solid plus some silver ion aqueous with zinc ion aqueous plus some silver solid. Okay. Our equilibrium constant expression for this one will just be these two items. No solids or liquids. In the equilibrium constant expression. Okay, so noticing that we have solid zinc and solid silver. Those do not appear in our equilibrium constant expression. And actually, I left something out. Sorry, this should have a squared there. Okay, so no solids or liquids. Next one. For this one, our equilibrium constant expression will just be CO2 times H2O. Right? Noticing we have solid sodium bicarbonate and solid sodium carbonate. And then our CO2 and our water are just gases. Gases are fine, right? It's solids and liquids. If you see an S or an L, leave it out of your equilibrium constant expression. Right, so our next topic, we're going to come back to dealing with combining equations and how to manipulate equations to combine them and how those manipulations relate to the value of K. Okay, so here we're going to be looking at the relationship of K to the balanced equation. Okay, so you might want to write down the headings of each of these. Okay, so this would be one of the headings that you might want to highlight in your notes. When you reverse an equation, you invert K. Okay, so take 1 over K if you have to reverse an equation in order to combine them in a certain way. Okay, so for example, if I have carbon monoxide gas plus 2H2 gas in equilibrium with some methanol. Sorry, it took me a second to come up with the name there. And it has a K value of 9.23 times 10 to the minus 3. Okay? If I reverse that equation and write it the opposite direction, okay, our second equation here is exactly flipped of the original equation. I'm going to write this and just call it, for differentiation purposes, K prime. K prime will be 1 over 9.23 times 10 to the minus 3, okay, which equals 1.08 times 10 to the 2. Okay, so if I need to reverse an equation in order to combine things, if I reverse it, I have to take the inverse of K, okay? And then my result will be the inverse of the original value. All right, the next thing to highlight in your notes, when you multiply an equation, raise K to that power. So previously, like when we were doing things with Hess's law and delta G and things of that nature, whatever you do to your equation, you do exactly to the value of enthalpy or delta G or S or whatever. When we're dealing with K, we have to deal with powers and inverses and roots and things of that nature, okay? So for example, if I take that same equation from above and I multiply it by 2, so if I say 2CO gas plus 4H2 gas equals 2 methanols, I'm going to say K squared. Okay, so all I've done is taken this reaction and multiplied it by 2. And when I multiply the equation, I take K to the second power. Whatever I multiply by, I take it to that power. So we would have our new K, K prime, is 9.23 times 10 to the minus 3 squared, which equals 8.52 times 10 to the minus 5. Okay. And the next thing, so if we multiply an equation, we raise K to that power. As you might expect, if we divide an equation, we take that same root. Okay, so if using the same equation, if I instead multiply it by 2, if I divide it by 2, if I say 1/2 carbon monoxide gas plus 1H2 gas gives me 1/2 methanol, then I'm going to say square root of K. Okay, so if I divided by 2, I take the second root. If I divide by 3, I take a cube root, so on and so forth. So our K prime to the square root will equal 9.61 times 10 to the minus 2. Okay, and then lastly, the bit of information, final piece is when you combine equations, multiply the K's. Okay, so when we were doing Hess's law and delta G and entropy, when we combined equations, we added those values. With K's, we have to multiply the values. This is a very common mistake in these problems, especially on exams, is that students try to add the K values together. It doesn't work. When you combine equations, you must multiply the K's. Okay? So let's do a specific type of problem. Let's utilizing these things. So let's say we want to know K for the following equation. All right, so we have the equation says N2O gas plus 1/2 O2 gas, we need 2 NO gas. K equals what? Okay, so what we can do is similar to previous types of problems. If I don't know K for this, if I know a reaction mechanism to get to this, and if I know the K's for those, then I can find the K for this particular reaction. So let's say you're given this equation and you're asked to find K, and you're given a pair of reaction mechanisms that might be manipulated in such a way to get this result. So let's say you're given these reactions to play with. You have to forgive me. Sometimes being left-handed wreaks havoc on trying to write on an iPad. That's why I'm constantly getting funny shapes and drop-down menus and things, because my darn left hand, though I love it, keeps getting in the way. And we know the K for this reaction is 5.4 times 10 to the minus 19. Right? And then we're also given another reaction that looks like this, plus O2 with 2 NO. And we're given a K for that. 4.6 times 10 to the minus 31. Okay, so you're given these two reactions, and we want to combine them to find the top reaction. Okay, so one of the first things that I can recognize is that my overall reaction, the one in green, has no N2 in it. Okay, so there's no nitrogen in that overall reaction, so I need to manipulate these equations in such a way that the nitrogens cancel each other out. Okay, so what I'm going to do is I'm going to take my top reaction and I'm going to reverse it. Okay, so if I get N2 on the right in my top reaction and N2 on the left in my bottom reaction, then they will cancel each other out. So I'm going to rewrite it down here. Okay, so I'll have N2O gas with N2 plus 1/2 O2. Okay, and since I've reversed it, now I need to invert the K for that reaction. One over the 5.4 times 10 to the minus 19. Okay, which will equal, looks like 1.9 times 10 to the 18. Okay, so given these two reactions, let's combine them and see if we have achieved our overall reaction that we have in green above. All right, so N2 on opposite sides. Let me come to a different color so this is easier to look at. Let's do a bright one. So the N2 will cancel each other out because they're on opposite sides of the equation. Right? O2s, the oxygens, are on opposite sides of the equation. Right? So if I have one O2 on top and half an O2 on the bottom, 1 minus a half leaves me with a half. So that one will go away and this will become 1/2 O2. Right? And I don't have anything else that I can manipulate. I'm not adding anything. There's nothing else that's the same on both sides. Right? So what I have left is N2O gas. Oops, excuse me, not yet. I still have the 1/2 O2. And 2NO. All right, and if I've done everything correctly and then combined correctly, this combined reaction should be the same as my desired overall reaction. It should be the same as the green one up here. All right, so now, in order to find K for this combined reaction, I say K prime times K. All right, so in this case, I'll have 1.9 times 10 to the 18 times 4.6 times 10 to the minus 31. Okay, so K for the overall reaction will come out to be 8.5 times 10 to the minus 13. All right, so I reversed the reaction, which forced me to invert K, and then when I combined them, I multiply the K's. Okay, I think I'm going to pause on the material at this point. We'll come back with a second video, starting with equilibria for gases in particular.